Okay, children. Today we want to discuss N-type and P-type semiconductor. Before that, you should know what is intrinsic semiconductor. Intrinsic semiconductor means pure semiconductor. Example, germanium, then silicon crystal, natural form. That is the intrinsic semiconductor. No impurities are added. And what do you know about the conductivity of intrinsic semiconductor? What do you know? Intrinsic semiconductor, we know the mainly two bands are there, valence band and conduction band. You can see in the figure. Valence band, you know, all the valence electrons will be there. We know silicon, germanium, outermost 4 electrons are there. When it form a crystal, neighboring germanium atom will be there and they will interfere outermost shells. Outermost shells of the atom will interfere and electrons will have different energy levels. And all the valence electrons will be occupied in the valence band. See, valence band. Valence electron. Valence electron is not free. They are attracted by the nucleus of the atom. So they are not free. If any electron come to the conduction band, they will make the material conducting. They can easily move, freely move in the crystal lattice and make the material conducting one. That is the case in an intrinsic semiconductor at a low temperature. So I will tell you, in an intrinsic semiconductor at very low temperatures about 0 Kelvin, semiconductor act as an insulator. Why it is act as an insulator? Here at a very low temperature, the valence band is complete. That means one germanium atom make covalent bond with neighboring 4 germanium atoms and it get 8 electrons in the outermost shell. So that is stable state. So at 0 Kelvin, it is in most stable state. All the valence electrons are bound to the nucleus and no free electrons are available for conduction. But you know, when 0 Kelvin to the temperature increases to even to the room temperature, and temperature increases to the room temperature from 0 Kelvin to room temperature. When the temperature increases, what happens? These electrons from the valence band will jump. Electrons from valence band will jump to the, you can see here, see, electrons from valence band jump to the conduction band.
Band gap to move into the conduction band and hence become free electrons. The vacant energy levels in the valence band create the opportunity of other valence band electrons to move into them. Therefore, in such solids, conduction is possible due to the conduction band electrons as well as due to the vacancies in the valence band.
So here you have seen when it get electron, when it get energy, how much energy it need to jump from valence band to conduction band? This band gap energy for a semiconductor, for silicon, for 0.5 eV is needed, but germanium 1.1 eV energy is needed for the electrons to jump from this is the higher level of energy level of electron, eV, and from here to this level to jump it need 1.1 eV. So less than 1.1 eV is enough in a semiconductor. Even at room temperature, the bond break and the electrons will jump from valence band to conduction band, and see some electrons are there down. Jump, 3 electrons jumped to the conduction band, and that can move freely in the conduction band and make the material conducting. At the same time, you can see the electrons are jumping and filling the hole. Electrons will jump and fill the holes created there. Here it was the hole, so electrons jumped to occupy that vacancy of electron. When 3 electrons jumped to conduction band, vacancies are created, and that vacancy is filled. That means the holes are moving. Vacancy filled means they are moving, holes are moving. What is a hole? H-O-L-E. What is a hole here? In a semiconductor, it is a seat of electron. Actually, it is a seat of electron. Electron when jumped, a vacancy is created. That vacancy of electron. Vacancy of electron is hole. And what will be the charge of hole? It will be positive charge, and magnitude is equivalent to that of electron. So we cannot tell it's a proton. Proton, it is not proton. It's only a vacancy of electron. Okay. Charge positive, equivalent to that of the electron charge, but we can't tell it is a proton. It's only a deficiency of electron, vacancy of electron created, an electron jump from valence band to conduction band. So in effect, what we can see, where at room temperature, what we can see, electrons are there in the conduction band, make the material conductive. At the same time, holes are there in the valence band, that also make the material conductive. Movement is there in the valence band also, the holes are moving. So actually, in the case of a semiconductor, both electrons in conduction band and holes in valence band make the material conductive. So when you find the current, the total current will be sum of electronic current plus hole current. Both you have to find out. And when you measure current, that will be due to the flow of electrons in the conduction band and the flow of holes in the valence band. Okay, though both constitute the current in a semiconductor. And you can see.
This is the reason why a semiconductor displays higher conductivity at higher temperatures. However, as the temperature decreases, we find that there are fewer electrons in the conduction band than at higher temperatures, and hence conductivity decreases. At the temperature of 0 Kelvin, the conduction band is practically devoid of any electrons, and as such, there cannot be conduction possible through the semiconductor. Hence, at 0 Kelvin, a semiconductor behaves as an insulator. This is the case of the semiconductor crystal. It is important to note that the band gap is different for different solids. Let us now look at the specific case of solids where the energy band gap Eg between the conduction band and valence band is very small, or the conduction band overlaps the valence band. When such an overlap occurs, the band gap Eg is nearly zero. In solids where a very small band gap exists, with no external energy available, there are no electrons in the conduction band. When a small energy is supplied, the valence band electrons move into the conduction band. Now let us look at the situation where the conduction band overlaps with the valence band. In this case, the valence band electrons are available to move into the conduction band and thus are readily available for conduction, which happens in the case of metals. Since a large number of electrons are available for conduction, the electrical conductivity is very high for such solids. We know that solids having very high electrical conductivity are called conductors. For some solid, there exists a very large energy band gap greater than 3 electron volt. In such solids, it is practically impossible for the valence band electrons to move into the conduction band, since the energy required is very high as the band gap is very large. Such materials then have very few conduction electrons and hence have very low electrical conductivity. Such materials are characterized as insulators. In semiconductors, we have seen that a finite but a small band gap of less than 3 electron volt exists, and as such, by supplying sufficient energy, the valence band electrons can move into the conduction band. Therefore, the semiconductors have conductivities between that of the conductors and insulators. Thus, we see that on the basis of energy bands, materials can be classified as conductors, semiconductors, and insulators.
Okay, children, here there is an important question. Based on the energy band diagram, differentiate conductors, semiconductors, and insulators. And you have seen here, in the case of conductors or in the case of metals, what happened to these bands? They either overlap each other. See, conduction band and valence band overlap each other. So what happens? Electrons are available in the conduction band for conducting. So metals are good conductors of electricity because electrons are available in conduction band. Otherwise, you know, a very small gap, either overlap or there is a small gap, very small gap between conduction band and valence band. Even in room temperature, electrons will be available in conduction band. That is the case of conductors. Example, metals. Then semiconductors, you see, the gap less than 3 electron volt. Less than, these values are important. 1.1 eV, I told you now, 1.1 eV. That is for germanium. If the germanium is taken as the semiconductor, its energy gap. Energy gap means this space no electron will be there. Highest energy level in valence band, lowest energy level in conduction band. Between the energy difference. Now, for example, suppose this is lower one is EV is 4 EV and EC is 5 EV. 5 EV minus 4 EV, that is 1 EV. That is the energy gap. Understand? So when the electron get energy, electrons in the valence band get energy 1 EV, it can jump to the conduction band and make the material conduct. So semiconductor, that band gap is less than 3 EV. And in insulator, you know.
Sir,
Yes.
can you admit Neelima?
Neelima. Okay. So in insulator, you know, this gap, this value you should remember. Energy gap in an insulator greater than 3 EV, about 6 EV is needed. Insulator material, rubber, plastic, wood, etc. Insulators. So the energy gap is very large. Energy gap between the valence band and conduction band is very large. So electrons find it difficult to jump from valence band to conduction band, and therefore no electrons are available in conduction band to make the material conducting one. Okay. It's an important question.
With conductors having a very small or nearly zero band gap. Semiconductors having a finite and small band gap of less than 3 electron volt, and insulators having a band gap of greater than 3 electron volt. A semiconductor without any artificially added impurity is called an intrinsic semiconductor.
So what is an intrinsic? Very important term. Intrinsic and extrinsic semiconductor. Intrinsic semiconductor means conductor without any artificially added impurity is called intrinsic semiconductor. Understand? Without adding impurity, without adding any artificially artificial impurity. The pure semiconductor, that is intrinsic semiconductor. Okay.
Both silicon and germanium, the two most commonly used semiconductors, exist as intrinsic semiconductors. Let us take a look at the atomic structure of silicon and germanium. Both silicon and germanium have 4 valence electrons. In crystalline form, each silicon and germanium atom uses its valence electrons to form 4 covalent bonds with 4 surrounding atoms. Let us use the crystal structure of silicon to further study intrinsic semiconductors. Remember, the following discussion applies equally to germanium in its intrinsic form. At absolute zero, all the covalent bonds in the crystal lattice of an intrinsic semiconductor are intact. Thus, at absolute zero, there are no free electrons to occupy the conduction band, and the intrinsic semiconductor behaves like an insulator. However, at higher temperatures, some electrons gain enough thermal energy to break free of the covalent bonds in the crystal lattice. These free electrons move to the conduction band, and the material starts behaving like a semiconductor.
So listen children, here what happened at higher temperature 0 Kelvin, no electrons are available in conduction band. It is all the, one silicon surrounded by 4 silicon atoms, and silicon need 4 electrons to make 8 electrons in the outermost shell. 4 already there, its valency is 4. So it need 4 more electrons to get 8 electrons in the outermost shell and to have stable state. So what it do when a crystal is formed? It share 4 electrons, one each from the 4 germanium atom. 1, 2, 3, 4. From the 4 germanium silicon, this is silicon. From the 4 silicon atom, it share 1 electron. One is its electron and one it share from this silicon. Like that, it make covalent bond. So what happen? 8 electrons it get. Outermost shell it get 8 electrons, and it is stable state when at 0 Kelvin. At 0 Kelvin, it very stable. All the electrons are bound to the nucleus. Valence band is filled. Conduction band is empty. When this is the case when higher temperature, electron jump. I told you valence band to conduction band electron jump. And how the electron jump, do you know? Because the bond break. So we have 2 theories here. One is bond theory, other is band theory. Understand? Bond theory, band theory. Both you should know. Bond, according to bond, B-O-N-D, covalent bond theory. According to bond theory, when it get energy at a higher temperature, when it get energy, one of the bond break. See, one bond is broken here and one electron is free. You can see, one electron is free. In that place, what is created? When one electron is freed or when electron get energy, it jump to the conduction band. So in that place, what comes, children? Ashlyn, what comes in that when the electron jump from one of the bonds? What is created? Ashlyn? Ashlyn, Arunjit? Arun?
Yes, teacher.
When an electron jump, when the bond break, electron is freed. In that place, what is created?
Positive charge.
പോസിറ്റീവ് ചാർജ് എന്നല്ലല്ലോ, ഞാൻ വേറൊരു പേരല്ലേ പറഞ്ഞെന്നേ. പോസിറ്റീവ് ചാർജ് ആയിരിക്കും അതിൻ്റെ വേറൊരു പേര് പറഞ്ഞില്ലേ? കേട്ടില്ലേ?
ശരി സർ, കേട്ടില്ല.
ഇല്ല. കനശ്യാം, വാട്ട് ഈസ് ക്രിയേറ്റഡ്? ഞാനൊരു പേര് പറഞ്ഞു, ഡെഫിഷ്യൻസി ഓഫ് ഇലക്ട്രോണിന് വേറൊരു പേര് പറഞ്ഞല്ലോ. കനശ്യാമുണ്ടോ? ഇല്ല. ആദിത്യൻ ഇല്ല. പിന്നെ ആരാ? അഭിനന്ദ് കേട്ടോ നോക്കട്ടെ. അഭിനന്ദ് ഇല്ലേ? Abhinand, when one of the bond break, the electron is freed to the crystal lattice and it can move freely in the crystal lattice. And what is created in its place? Holes. അതാണ് holes എന്നാണ് പറഞ്ഞത്. HOLE. Hole is the deficiency of electron and HOLE. and അവിടെ ഒരു ഹോൾ ക്രിയേറ്റ് ചെയ്തു. അപ്പോൾ അതിന് ചാർജ് എന്തായിരിക്കും? പോസിറ്റീവാണ്, പോസിറ്റീവ് ചാർജാണ്, ഇക്വാൽ ടു ദാറ്റ് ഓഫ് ഇലക്ട്രോൺ ആണ്. പക്ഷേ അതിൻ്റെ പേര് നമ്മൾ ഹോൾ എന്നാണ് പറയുന്നത്. HOLE, ഹോൾ ഈസ് ക്രിയേറ്റഡ്. ഓക്കെ, ഗുഡ്. So here electron is freed and a hole is created here. And you see hole is a positive charge. Actually, positive, its charge is positive. When electron is moved from that part, it gets a positive charge. Value will be equal to that of electron, but positive. And what about other bond, these electrons, when it will be attracted to these holes, because their charge is positive, so the electrons will be attracted to that. So the one of the neighboring bond will again break. One of the neighboring bond break and that electron will move to fill this hole. One of the neighboring bonds break and fill this hole. അപ്പോൾ ഇവിടെ ഒരു ഹോളായി. അപ്പോൾ ഇവിടെ എന്ത് ചെയ്യും? ഇവിടുത്തെ ഇലക്ട്രോൺ will be attracted to this hole. ഇവിടെ ബ്രേക്ക് ആവും. അങ്ങനെ holes are moving at the same time electrons are also moving in the crystal lattice. So both make the material conducting. അപ്പോൾ അതാണ് ഇവിടെ കാണിച്ചിരിക്കുന്നത്. Electrons jump from valence band to conduction band and here holes are there. ഹോൾസ് കണ്ടോ വരച്ചിരിക്കുന്നത്? ഈ ഗ്രീൻ കളറിലുള്ളതാണ് ഇലക്ട്രോൺസ് ആക്കി വരച്ചിരിക്കുന്നത്, ബ്രൗൺ കളറിലുള്ളത് ഹോൾസ് ആണ്. അപ്പോൾ ഇൻ വാലൻസ് ബാൻഡ് വി ക്യാൻ സി ഹോൾസ് and in conduction band we can see electrons. Both the make material conducting. അപ്പോൾ conductivity ഇതാണ് ഇൻട്രിൻസിക് സെമി കണ്ടക്ടറിൽ ഹയർ ടെമ്പറേച്ചറിൽ നടക്കുന്നത് കേട്ടോ. ലോവർ ടെമ്പറേച്ചറിൽ only electrons valence band, only electrons are there in valence band, no electrons in conduction band. Higher temperature this is happening. Higher temperature bonds break. Bond theory പറയാൻ പറഞ്ഞാൽ എന്താ പറയുക? One of the bond break, electron is freed to the crystal lattice. It can move freely in the crystal. At the same time, holes also are moving because the other bonds break, occupy that place. In that place, a hole is created. Again, another bond break and electron come and occupy that vacancy, and another hole is created here. Like that, holes are moving along with the electrons which are also moving. So both the make material conductive. Children, when I play the video, are you able to hear properly? Please tell the answer. Are you able to hear it clearly? Or it is not clear? Please tell. Ismail? Ismail is not there? Nandana?
Yes, teacher.
Are you able to hear the when video is played?
Yes, teacher.
Clear it is?
Yes, teacher.
Okay.
Note that each electron that moves to the conduction band leaves behind a vacancy in the valence band. This can be visualized as breaking of a covalent bond, where an electron becomes free and leaves behind a vacancy in the covalent bond. An electron breaking away from a covalent bond takes away a unit negative charge with it. leaving behind a vacancy with an assumed unit positive charge. A vacancy with a unit positive charge in a covalent bond between atoms of a semiconductor is called a hole. Thus, whenever a covalent bond is broken in an intrinsic semiconductor, a free electron and a hole is created. We refer to this as an electron-hole pair. Hence, in an intrinsic semiconductor, the number of free electrons is always equal to the number of holes at any given moment. Consider a hole or a vacancy at position 1 in the crystal lattice of a semiconductor. Now, an electron from position 2 can jump to occupy the vacancy at position 1. This fills the vacancy at position 1 but creates a vacancy or a hole at position 2. Similarly, an electron from position 3 can jump to occupy the vacancy at position 2. This fills the vacancy at position 2 but creates a vacancy or a hole at position 3. As a result of such jumps of electrons across covalent bonds, the holes or vacancies appear to move across the crystal lattice of a semiconductor. Note that the movement of holes occurs because of the movement of electrons across covalent bonds in a semiconductor, and not because of the movement of free electrons. Thus, there are two types of moving charge carriers in the crystal lattice of a semiconductor: the negatively charged free electrons and the positively charged holes. When an electric field is applied across a semiconductor by connecting it across the terminals of a battery, the free electrons move towards the end connected to the positive terminal and generate an electron current denoted by IE. The holes shift towards the end connected to the negative terminal and generate a hole current denoted by IH. The total current flowing through the semiconductor is equal to the sum of the electron current and the hole current. If a free electron collides with a hole, it fills the vacancy in the covalent bond without the generation of any other hole. This is called the process of recombination. Under thermal equilibrium, the rate of generation of free electrons and holes in a semiconductor is equal to the rate of their recombination, so that the density of charge carriers in a semiconductor remains constant. As we learnt earlier, a pure semiconductor without any impurities in it is called an intrinsic semiconductor. Both silicon and germanium exist as intrinsic semiconductors. There are two types of charge carriers in the crystal lattice of an intrinsic semiconductor: the negatively charged free electrons and the positively charged holes. The conductivity of an intrinsic semiconductor increases with rise in temperature, as more number of electrons break away from the covalent bonds of the semiconductor atoms. However, at room temperature, intrinsic semiconductors have very low electrical conductivity. The electrical conductivity of an intrinsic semiconductor can be improved by increasing the number of free electrons or holes in it at room temperature. When a small amount of suitable impurity, say a few parts per million, is added to an intrinsic semiconductor, its conductivity increases to a large extent. A semiconductor that has an added impurity to increase its electrical conductivity is called an extrinsic semiconductor. The process of adding the suitable impurity to a semiconductor is called doping. Thus, an extrinsic semiconductor is also called a doped semiconductor. The impurity atom added to a semiconductor to increase its electrical conductivity is called a dopant.
Okay, children. So, intrinsic semiconductor, which are the charge carriers? Electrons and holes. And number of electron will be same as number of holes. Both constitute current, and the total current is IE electronic current, IE plus hole current, IH. So, these are all important equations. Total current I equal to IE plus IH. Rate of generation of holes and electron will be same as rate of recombination. That's why Na becomes equal to NH, and total current is I equal to Ia plus IH. So, even though as temperature increases, the conductivity is increasing in a semiconductor. But you know, its conductivity is very low. When temperature increases, conductivity is increasing. But conductivity is very low. For practical purposes and all, we cannot use it for practical purposes because of its low conductivity. So, we have to improve the conductivity of intrinsic semiconductor. So, what is done? Impurities are added. Suitable impurity, not any impurity, suitable impurity. Here impurity means it is another element. We are adding another element. For example, pentavalent element or trivalent elements are added. Pentavalent element is example antimony, arsenic, bismuth, etc. are pentavalent impurities added. And trivalent, see, trivalent indium, boron, gallium, etc. are trivalent impurities. Impurities means that are another elements. Suitable impurity, suitable means size of the atom should be almost equal to size of silicon. Silicon is having 4 valency. So, that means trivalent will be to the right side, pentavalent will be to the left side. That means just near their neighbors. And the periodic table you can see that tetravalent, or means this germanium and silicon is in between pentavalent and trivalent elements. It is having 4 valency in between that. So, its size will be almost same. Size of atom, atomic size of pentavalent and trivalent will be almost same. So, similar type atoms should be added. That is one important thing when you add the impurity, almost equal to that of the size of the intrinsic semiconductor. That means germanium or silicon. But that impurities are called dopants. You can see here dopants. And intrinsic semiconductor. This is intrinsic, low conductivity. And after adding impurity, we get doped semiconductor. So, what is the doping? Adding impurity to the pure semiconductor. Why we are doping it? Because pure semiconductor or intrinsic semiconductor conductivity is low. That's why we are doping it. And by doping, what happened? Conductivity increases. So, that conductor is also known as extrinsic semiconductor. Intrinsic means pure semiconductor, no impurities are added. But what is extrinsic semiconductor? Impurities are added to it. For what purpose impurities are added? To improve the conductivity. Understand? Doped semiconductor or extrinsic semiconductor. Okay. The next you can see.
During the process of doping, the dopant gets positioned in the crystal lattice of the semiconductor. It is important that a dopant does not distort the crystal lattice of a semiconductor. For this, The dopant atoms of the semiconductor crystal should be comparable to the semiconductor atoms in size. We have learned that both silicon and germanium are tetravalent. That is, each of their atoms has 4 valence electrons. Commonly used dopants are either trivalent or pentavalent neighbors of silicon and germanium in the periodic table. Commonly used trivalent dopants that have 3 valence electrons are boron, aluminium, and indium. Commonly used pentavalent dopants that have 5 valence electrons are phosphorus, arsenic, and antimony. The addition of trivalent and pentavalent dopants creates 2 different types of extrinsic semiconductors. We know that in crystalline form, each silicon and germanium atom forms 4 covalent bonds with 4 surrounding atoms. When a trivalent dopant, say an aluminium atom, is added to a silicon semiconductor crystal, the aluminium atom occupies the same position of a silicon atom in the crystal. A trivalent dopant atom forms covalent bonds with 3 neighboring semiconductor atoms. However, the dopant atom has no electron to share with the 4th neighboring semiconductor atom. Thus, a vacancy or hole is created in the lattice. Each trivalent dopant atom creates 1 hole in the crystal lattice of the semiconductor. At room temperature, some of the electrons break away from their bonds, giving rise to electron-hole pairs. Simultaneously, some of the free electrons recombine with the holes and reduce the number Ni of intrinsically generated electrons to Ne. Thus, the number of holes in a semiconductor doped with a trivalent dopant is much larger than the number of free electrons in it.
Listen, children. So here, when dopants are added, what happened? Aluminium. See, it occupied. Earlier, it was silicon. Everywhere, it was silicon. But when dopants are added, here aluminium is added as the dopant impurity. So in the place of silicon, that aluminium occupies. So you can take this aluminium atom, and it is having only 3 electrons in the outermost shell. Aluminium is having 3 electrons in the outermost shell, trivalent impurity, 3 electrons. So what it do? With the 3 electrons, it will share with the neighboring silicon, 1, 2, 3. When, with the 3 neighboring silicon, it share 3 electrons. But the 4th one, this is also silicon, 4th one need, there is no available electrons with aluminium to share with this silicon. So what happened? A hole is created. Hole is actually a vacancy of an electron. And what happened? When a hole is created, what happened? It is a positive charge. So other bonds will break and will come and occupy this here. So when 1 aluminium atom is added, 1 hole is created. So if 3 atoms are added, 3 holes are created. So depending upon the impurity atoms added, impurity atom added, that much number of holes will be generated. Depending upon the impurity. If 3 atoms are added, 3 holes are created. 3 holes excess than the intrinsic semiconductor. Intrinsic, we know both numbers are equal. Number of hole equal to number of electron. But when a trivalent impurity is added, which number increases? I'll ask to Akshaya. Akshaya. When a trivalent impurity added, which one is increasing? Number of hole or number of electron? Number of hole or number of electron increases? Akshaya.
Number of holes.
Number of holes increases. Very good. So we tell number density of hole is greater than number density of electron. Number density means number of electrons per number per unit volume. That is number density. So number of holes is very much greater than number of free electrons. That is happening.
We learnt earlier that a positive charge is assumed to be associated with holes. Thus, positively charged holes act as majority charge carriers in a semiconductor doped with a trivalent dopant. Thus, such extrinsic semiconductors are called p-type semiconductors. In spite of having the number of holes NH greater than the number of free electrons Ne, the p-type semiconductor crystal remains neutral, as the charge of the additional charge carriers is equal and opposite to that of the ionized cores in the lattice. The movement of holes as charge carriers occurs when valence electrons from neighboring semiconductor atoms jump to fill the holes created by dopant atoms in p-type semiconductors. When a valence electron fills the hole generated by a dopant atom, the dopant atom becomes negatively charged. Thus, a dopant atom in a p-type semiconductor is called a negatively charged core or an acceptor impurity. A p-type semiconductor has an acceptor impurity energy band that lies just above the valence band. Thus, the free electrons can leave the valence band by covering a much smaller energy gap as compared to an intrinsic semiconductor.
So here we have seen that a new energy level is formed because more holes are created. Understand? So the electrons will jump from valence band to this new energy level. Electrons are jumping, and in that way the more holes are created. So a new energy level is formed, that is acceptor impurity bond or acceptor energy level, impurity band, acceptor energy level just above the valence band. You have to see that it is not near to it, it is just above the valence band. So new energy level is formed, the energy gap, now you see the electrons can easily jump to this level, energy level. So here more holes will be created and electrons will be in this band, new energy band. Understand? So here p-type semiconductor, a new energy level is called acceptor energy level is found. Why it is called acceptor impurity? Acceptor, it is accepting. It is actually when aluminum is added, a hole is created. Deficiency of electron is that. So it is accepting electrons. So that's why it is called acceptor impurity. Okay.
Semiconductor. Valence electrons in p-type semiconductor can move from the valence band to the acceptor impurity energy band even at room temperature to create holes in the lattice. Thus, electrical conductivity of a p-type semiconductor is much better than an intrinsic semiconductor.